Hello, everybody, and welcome to the YouTube Mall Builders Arduino workshop with Chris Heili from MRL Trains tonight. Chris got another good show for you. Just to let you know to go to YouTubeMallBuilders.com. There you can get all the latest info on schedules. You can check schedules for the Tuesday, Wednesday, and the Saturday live shows, and check your time zones for when the shows are going to be live. And if you happen to miss a show because you're working or didn't get the time zone calculated right, that's okay. They're recorded. You can go to YouTube Mall Builders on YouTube. We have playlists so that you can select the right show and be able to watch it all the way through. We do appreciate putting comments down in the comments area. Let us know how you like the show or if you had any questions or anything. So give us the comments. We need them. Like know how we're doing and what we need to change. Also, while you're there at YouTubeMallBuilders.com, be sure and click on the e-magazine. There you can sign up for the get on the mailing list so that when the e-mag comes out, you'll be able to get your copy of it as a PDF, and that way you watch it on a wide variety of devices. I'll say watch or read it, and doesn't matter where you're at, you have the e-mag with you for some interesting reading. JD and his crew do a great job on that magazine. So, all right, I guess I'll go ahead and turn it over to Chris now, and let him have the show. So it's all yours, Chris.
All right, thanks, Johnny. Welcome back, everybody, to our next Arduino workshop. Have a little bit of show and tell like we talked about last week first, and then, and after we're done with the show and tell, we're going to cover buttons, which are just the little push buttons that you can use to activate things. And while it seems like it might be something simple, there's a little more to them than you might think if you haven't looked at them before. So I always spend the night doing 3 or 4, maybe 5 exercises with push buttons and learning all about those. So with that, I'm going to go ahead and welcome to JD, Lloyd, Johnny, Dave, Andrew for being here tonight. And I guess we'll start with JD, I guess, with his show and tell if you want. JD, you want to jump in and go ahead and show us what you got?
Sure. Thanks, Chris. First of all, let me show it working. What I'm basically using is an ultrasonic sensor to control flashing lights and a servo motor to control gates. This Bachmann piece right here with mechanical gates, just hooked up with fishing wire or fishing line. And when a train crosses the sensor, basically the lights flash and the gates go down. And they'll stay flashing as long as the sensor is blocked by a moving train. So, and then if I go further away, eventually the gates will come up with a little bit of delay. And I'll get into that in a moment. And the lights will flash until the gates are up and the cycle finishes. Let me quickly share with you guys the wiring diagram because it's very difficult to see what it looks like right here. Just give me a moment, I'll bring that up. So, Chris, until you told me there was a tool to draw, I was using Microsoft Word to draw this at Publisher. But anyway, here's your Arduino board, your breadboard, your ultrasonic sensor right there, and your servo motor. Basically, your power, your 5 volts to the positive rail, your ground to the negative rail. And then I connected the servo motor, the control pin, to pin number 6 on the Arduino board on the digital side. And then for the echo, there's 4 pins on the ultrasonic sensor. There is the ground and the power, which red goes to the power here rail, and then the ground goes to the negative. Same thing with the servo motor, the ground goes to the negative, and the VCC goes to the positive on the rail, so it's picking up power from there. The other two pins, one is trigger. That one sets the trigger for the control for the ultrasonic sensor. And then the echo pin is what you read to get back the echo. So the trigger pin is an output, the echo pin is an input in this. And those are the two control mechanisms for reading and triggering the echoes or a ping off of the sensor. The left side here actually sends out the ping, and then the right side receives the ping, the echo back. The other thing that I did was the two flashing LEDs to indicate the lights on a signal. I just didn't have the time and the tiny LEDs I needed to hook up into this the gates. That would be my next thing to do. But pin number 5 and pin number 3 are those for that. And of course, you know, the resistor goes from on the anode, which is the positive side of the LED. That's actually the longer leg. And then the cathode side, the negative side, goes into the negative rail to complete that circuit for both of them. So that's the drawing for the wiring. And then let me kind of take you through the code real quick. And as we do, bear with me 1 second. Just trying to find the monitor. It's hard to. It's hiding. There you go. So you'll see where that comes in a moment. Okay, so one of the first things that I did was I included the servo library, because that's what you need to control the servo. And then I defined all my variables at the top. Here's all my pins right here. So I like to group those together. So my control variables. One of the things that I do is track the state of the signal. Is it either on or off? That means the gates are lowered or not lowered or raised. So 0 is off. That means they're raised. And so it has not been triggered. So pulse counters I use to count for false positives. One of the things that I've noticed about the sensor, as you will see every now and then, you will see a count of 1 show up in there instead of me displaying how many inches. So if you look at that scrolling up, you'll see that that's a false positive. And what I can do is I can control that easily by how many times I want to count right here. So if I change that to 8, I'm going to at least get a hit 8 times against the sensor to make sure that the distance that I want to compare before I trigger this has been met at least 8 times. So now, right now, it's set to 5. I was talking about 8. Right here's that variable right here. So what I'm saying here is that I want to start the signal if my echo that returns back is less than or equal to 8 inches. All of these are float types. One of the things that's important to understand in this language, as well as in Arduino, is that data types matter. And if you're getting a number back from the sensor, you're going to get back in microseconds. So you have to do some math on it to convert, and that all has to be floating point math in order for it to work correctly. So some of the things that you need to understand to convert to inches, I wanted to convert to inches. I could convert it to scale miles, but for just simplicity, I converted to inches. So some of the numbers in here: inches in a mile, how many seconds in an hour. I want to track my ping duration. How long did it come? I'll compute that from the sensor, and my target distance, and I'll eventually have in inches the total target distance that I'm currently displaying as you see it going by. The speed of sound matters. Apparently, the temperature also matters to the sensor. If it was cold, I was getting a much higher rate of false positives than it was warmer. So this is at 77 degrees. That's the speed of sound. So you could actually look that up online in Wikipedia and find those numbers. The servo angle, that's the angle that I want to track as the gate goes up. And then what I want to say is these are my ranges. I want to go from 10 degrees to 90 degrees. And again, adjustable here. And then the distance that I want to start comparing at to start my gates from lowering and raising. I declare my servo motor, call it my gate motor, and then I set up my pins. Notice the input for the echo pin. Everything else is output, but this is what we're reading to get the echo back. And this data comes back in microseconds. So I go ahead, attach my motor, and then I immediately make sure that the gate's raised from the beginning. So on the get-go, the gate should be raised. The assumption is there's no train there. I go ahead, write the trigger pin low. So we want to catch the high pulse. So we set it to low. We do, this is noticed in microseconds. The digital write returns it in the pin in microseconds. So we want to delay in this case, and again, you can change these numbers around and test, 2 1,000ths of a second here. So that's 200 for delay microseconds rather than the delay command. And a digital write pin high, and now we just want to wait 1/100,000th of a second for a very, very small delay. We don't want to ping forever. And then we put the trigger back to low. So it's a low, high, low pulse that we want to capture. Now then we go through some math to figure out converting from microseconds into miles per hour, and then that into the duration in miles per hour and the distance. So one of the things you have to remember when it's pinging, it's sending the signal out to the target, and when it comes back, that's twice the distance. So you got to divide by 2 right there. Otherwise, you'll get a different number. And then what we multiply by inches in a mile, and it's just taking this. It's like saying x is equal to x times this. So we're just taking the same variable, putting the number right back in that we're reading the old number from. So now my target distance has the distance in inches, and that's what I'm displaying right there that you're seeing on the screen, scrolling up. So I'm comparing, showing my versus the 8 inches that I've set up as my target. So notice that false positive just go by. And the logic is I'm tracking that signal state. So first thing I'm doing is I'm checking to see if my signal's on, then I want to continue flashing. One of the things you have to remember is that this is in a loop. It's in a forever loop. So you got to program that way. So this if is mutually exclusive by the virtue of the fact it's either on or off. So if it's on, I want to continue flashing my lights. The assumption is the gate is down at that point. There's 2 sets of if logics. One's for lowering the gate and one's for raising the gate. And there's nested ifs in here. So the first thing I want to do is I want to check to see that if my target distance is less than the starting signal distance, which was 8 inches. So my target distance is what I just computed. And is it less than 8 inches? And what I'm going to do is I'm going to put a ruler here against this thing. And then I'm going to take something and I'm just going to slide it. And we can actually see, and I think I triggered it too. So to let it finish lowering the gate. Can you see that scrolling or no?
No, you're in screen share.
Yeah, but I just want you to see the inches. I can't screen share and show the visual. I'll come back and show the visual in a second. So all I'm doing is taking a ruler and I'm just sliding it across from the front. Let me stop sharing for a second. Okay, so here's a ruler, and I'm just sliding this piece right here. And so my readout shows the number of inches that I'm at. And now that I'm under 8 inches, you notice the gate's triggered. As long as I stay within this 8 inches, the gate's going to continue being lowered, and the lights are going to continue flashing. But if I go further back, the gates will eventually come up. And then the lights will eventually stop. The lights stay on, to be prototypical, the lights stay on until the gate fully raises. So I compare the distances, and I pretty much off by almost 1/8 of an inch. And it just depends on where you're putting the ruler at up against the sensor. So let me go back to screen share.
Hi, JD.
Yes.
Let me read a comment before you get any further.
Okay.
We're turning my mic back over. All right, you got a comment from James Luger. Of course.
Okay.
He's right about this. I think I would use a light-dependent resistor in track to sense the train on either side of the crossing, and that's what most people would do.
Say that again. Can you say that again, John? Sorry.
He said he would use a light-dependent resistor in the track to sense the train on either side of the crossing.
Yes, you can do. There's a couple ways you can do this. You can use a infrared sensor, you can use a photocell, or you can use this, or you can use another type of sensor to trigger a pressure sensor. So there's many ways of doing this. This is just one way of those many ways.
Yeah.
I wanted to play around with the ultrasonic sensor, so that's what I chose to do. Photocell, you know, if you have a night scene, may not work.
Yeah,
whereas an infrared sensor would.
Yeah. I got one more comment, and I'll let you get back to it. Could you do the switch statement for this instead of a nested ifs?
You could. You could test for, you know, a condition. You could set that up on the top, and you can do a switch statement, sure. But it's, you know, it's only a single set of nested ifs. Actually, I take that back. You could not do a switch statement, and I'll tell you why. One is dependent on the other. The nested ifs is a tertiary condition, and you'll see in a moment why.
Hey, JD, if I could step in. I took a slightly different approach with my coding, and I did use a switch statement. I'll show you that in a little bit when we go through mine.
Right. In my logic structure, you know, the way I was thinking, one is dependent on the other. And that's particularly for false positives, just to, you know, make sure that it is a train going by, so you don't get, you know, false hits. And so what I'm doing here is I'm comparing the distance. Okay, so if it's been triggered, but the signal has to be off, right, in order for it to get turned on. So signal state must be 0. So both have to be true. And if that's the true, I go ahead, increment the pulse counter for the down, lowering the gate by 1. Okay, and I go ahead, show that. And that's what you see that 1 go by, the false positive right here. Now, what in the nested if, I check is the pulse counter down greater than my number of times I want to check, right, which is 5. If that's the case, then I go ahead and do the logic of lowering the gate, okay? And then I'll come back to the logic in a second. And then I set my signal state to 1, that it's been now lowered and the flashers are on, and then I reset the pulse counter. Otherwise, it's a false positive, I go ahead and reset the pulse counter and don't touch the signal state because it's already 0 at that point. So in here, in the nested if, what do? I take a for loop. Basically, I gave it fancier names, gate, angle, position. So this is this raised angle that I declared up above. And that's 10 degrees. And then I check that against to see the lowered gate servo angle, which was 90 degrees. So once we reached 90 degrees, or I'm sorry, working from 90 degrees back down to 10 degrees, and I actually subtract by the number of degrees I indicated up above, which was declared as 5 degrees. Okay, right here. So I can change by how many degrees I move the motor to how smooth or how rough I want it. Okay, so I wanted the speed to be slow like a prototypical gate, so that's why I chose 5. Let's see, right here. So it's jumping.
That's,
you know,
pretty cool, JD.
That's a shot.
Good work going on here.
Pardon?
That's pretty awesome. Good work you've done here.
Thank you.
I think it's interesting because I know some of you guys out there that are the beginners are probably looking at this going, "What in the?"
Yeah, I got a little fancy with it.
The cool thing about this, though, is it shows that we took a guy who was a computer programmer that never messed around with the electronics end of it. Now we just married him to the electronics, and look at what he did in a couple weeks.
Actually, in about 2 or 3 hours time.
Coding, so. Yeah, so to the other half of the equation, the electronics to go along with his programming ability. This is what he's able to do. So.
Yeah, and you know what?
I'll get there, but probably not.
You build your code piece by piece. You know, you add more fancy stuff to it. Build the basics first, and then you add fancy stuff to it.
All right, Chris, I've got a couple other comments.
All right.
So anyway, this is the light flashing, and then this is the actual motor, right, the position. And I had a delay in here, but I set it to 0. So if I wanted to put a delay, I can. There was no need to. And then you saw this already. So the raising of the gates is not exactly similar logic, but the only differences are that you're working in reverse and you're checking to see if the signal is on, and the less than equal becomes a greater than here, right? Same thing, you're doing an up counter for false positive. Same kind of setup here, erasing the counter back to 0 if you got a false positive, and then setting the signal state back to 0 instead of 1. And it's a separate counter for going up versus down. And the only other difference here is I'm doing the motor first and then flashing the lights. And once that loop is done, I flash the lights one more time after raising the gate.
Okay, I guess we got some comments. So, Johnny, you want to jump in with those comments for a second?
All right. Way JD had all set up, people were asking, could you achieve the same thing off the block detector setup? Yeah, using block detection. Another one here from Steve. That was Robert. This is Steve. I would use the current sensor in the block before and after the crossing.
Yeah, you know,
that's.
Go ahead.
Yeah, that's another one that we, are going to get to sooner than later is block detection by current sensing and then tying it in. So that would, that's just another method that we haven't even approached yet. So.
But you were talking also about the photo sensor on either side of the track. My scenario that we'll go through in a minute has that, and so I'll show you that as well. So we'll get to that point.
And just so you know how I'm moving this cheap, basically $20 Bachmann thing, is I'm using fishing wire or fishing line, 10-pound fishing line, which you cannot even see it.
Nice.
You can see the one gate, it's not as hot as I wanted it to be, so it doesn't raise and lower as much.
And but I see where your servo is heading there on the end of your breadboard. Very interesting. Well, thanks for sharing that, JD. That's pretty awesome. And hopefully someday we can all get. I see many years of programming that after that someday, but I don't think I'd ever be able to do all of that. So, I do believe. Did you say you weren't able to get to one, or did you have something you wanted to share?
For who was that?
Lloyd. I think he wasn't able to get to one. So let's jump over to Andrew.
Sorry, Chris. No, I didn't have time to do anything, but I'm getting prepared for my speedometer.
Yeah, that's going to be really neat when you get done with that. Can't wait to see that one.
Yeah, and the other thing,
let's jump.
You can display the speed, on a display. That would be another thing you could do with this.
Yeah, absolutely. Or even the distance for some. Well, you calculate the speed from the distance.
Approaching distance, to calculate the distance, exactly.
Okay, so we got a new panel member tonight, Andrew. Did you have something you wanted to share with us, Andrew?
Yeah, mate. If I can share my screen, I don't know why I have to do it. No, I've got to do it. Get ready. Let's see if this works.
All right. Yep.
All right, you see that? They're showing up probably full screen. Basically what I've got is, this is going in my control panel. It's not showing up on my screen.
I'm still saying JD here.
Yeah, Andrew, I see mine up on your screen.
Sharing your...
Should be able to see my workbench.
No, we're seeing... now locked up. Okay, well, I'll tell you what. We'll jump to somebody else, let you get that straightened out, and we'll come back to you. How's that?
Yep.
How about the other Andy? You got anything you wanted to share tonight?
Yeah, as soon as my mouse will kick in and unmute this thing. My stuff's what I've been doing is kind of related to the buttons. But you're going to kind of go through that tonight. That the intent's to go through buttons. Okay, then let me just show it as we go along. That way I'm not getting ahead of anybody, and that way you can cover the basics before I, before I go confuse anybody with my button configuration.
All right. Well, we'll save you till after we do buttons then. How's that?
Yeah, that'd be cool because I've got a board with numerous buttons that and the sensors we used last time, but it's easier to show once people have seen the basics because the big one thing I'm happy about what you're doing here is that it's not. I agree. You don't have to go too far, and this is not as complicated as it feels or sounds sometimes. So I don't want to daunt people with. I promise what I've done is not that complicated, but.
Okay, looks like he's refreshing. So I'll jump in there in the meantime, and I'll start sharing what I did. Mine is a little bit off topic. I know I asked you guys to stick to the things that we covered so far, but I had very little time to work on anything in the last 2 weeks other than my layout, but we did have a hangout middle of the week last week, and I discovered I was able to connect my Arduino to JMRI and get it to talk with JMRI, and I thought that was cool because that's something I've been looking for. That's the whole reason I dove into Arduinos. So I'm just going to show you real simply what I did, and this is going to actually be a future show because I think this, we want to stay railroad related in everything we do, and this is absolutely railroad related, connecting to JMRI. So I'm going to show you real quick on camera, and then I'll go. But if you notice right now, you're just going to see. Oops, there we go. Loose connection. Red light, green light. What that is it's toggling back and forth. What I'm doing is I'm in JMRI and I'm throwing a turnout. And those two lights, I don't have a bi-color LED like you would have in a searchlight. So I just simulated it by using 2 LEDs. But this is basically a turnout. If it's clear straight ahead, it's green, and there would be another light below it that would be red for the diverging route. I didn't get that far. I only had time to work with one. This simulates one signal head where you'd have 2. But then, of course, when you throw the turnout going straight ahead, you'd get a red light and then below that you would have probably a yellow or a flashing yellow for. So basically, as I throw that turnout back and forth, this is simulating a single head on single searchlight. But now I'll share my screen quick and show you what it looks like in JMRI, and then I'll show you the code, which is super simple. I was amazed at how simple it was. Here we go.
And Chris, you had to add any kind of libraries to that?
Yeah, there is a CMRI library, and we'll get to that in a second. So can you see this is my a simple layout panel I made using JMRI. Are you able to see that? I had problems last week too with my screen sharing. It's like Andrew's not the only one, so try it again. There we go. Now I know it's working because now I got the tunnel of doom. There. Okay, so I just threw together a real quick and simple single turnout. Well, actually, it's just like a passing siding. And tied the sensor to the turnout so that when I click on the sensor, it throws the turnout. And I got as far as putting all these lights in for a single turnout. This particular head right here, if you watch, it's green when you go straight through, and it's the diverging route. This is the other head that I don't have simulated that I was telling you about. So those 2 LEDs are just to simulate this one right here, and all it does is, so I created a sensor, I created the turnout, I created the signal heads, and then using a CMRI library and a CMRI, which is Bruce Chubb's computer model railroad interface, was actually able to connect to my Arduino using a CMRI connection. Just like if you had an NCE system, you use an NCE connection. It'd be a Digitrax connection. So I got to tip my hat to Chris Rude, who was the guy who turned me onto this, and it's the links out on the Google Plus page if you guys are interested in this. It turned out to be fairly simple. We had a couple guys got together in a normal hangout, and we just kicked through this, and I think I was the only one who was able to successfully complete it that night before we hung up, but I think subsequently Andy and a couple other guys were able to get it working for them too. So looking forward to really being able to dive into this and do a whole lot more with it. But what I'm gonna do is show you my Arduino sketch, that what it takes to do that. Actually more in this sketch than what it's doing, because I was starting to build it for the more lights. But at the very top of the sketch, it says include CMRI. That's the library you have to download, and that's where the link that Chris Rude posted. And I'll post it again after the hangout on our Google Plus page, and maybe even on the YouTube comments. Playing around and getting this working before we get to this in a couple of weeks. But you load the CMRI library and then a CMRI command. Setup, you're simply telling the serial monitor to begin. It's because you could actually watch this on a serial monitor if you wanted to. Then I'm just defining 2 pins, pin 13 as outputs. And then I get to my loop, and all it does is it executes this CMRI process. That's from the CMRI library, and it just, the next line of code says digital write 13. So actually all it's doing is it's going out, it's polling pin 13 to see what its state is, and then it's turning on or off the LED accordingly. Then I'm doing the same thing for the other LED. So these other 2 ones were for LEDs I didn't finish and put on yet. So really, if I can just delete these, this line of code, everything you see right there is all it takes for me to do that. So that's just crazy simple. You hook it up to CMRI, just a little bit of a learning curve in JMRI, but it was very little. I mean, if you've used JMRI before for layout panels or connecting turnouts or anything, it's really no learning curve at all. So yeah, I'm pretty excited about being able to do a lot more with this in the near future. So that's my show and tell for tonight. I'm going to stop sharing, and we'll up and running yet.
By the way, I was able to, while I got just a second, I was able to get my CMRI working. We'd figured out it's a version. If you're on the 4.1.6 or whatever the newest version is, and you're interested in the CMRI stuff, there is some issues apparently with it. And going back to the version 3, the last release of version 3 fixed that for us. So just kind of a heads up to anybody who wants to start playing with it. And then my last sentence is I really look forward to us getting another hangout of doing some CMRI stuff, because that is absolutely fascinating, guys.
Okay, and I'll tell you, I looked since you told me that, and I'm running 4.0, like 4.0.6 or something like that, and it works for me. So I don't know what the latest, I haven't downloaded the latest in probably 1.5 years now. So
well, there was 3 of us.
Versions.
Right, there was 3 of us that had found that to be the problem. But 4.1.6 was there's an annotated problem in their release notes for that version. But I don't know how many versions back you had to go. But they still had a copy of version 3.11 or whatever out. So I rolled a copy of that on one of my other computers just as a test case. But I may need to look at, maybe I don't need to go back multiple versions. Maybe I just need to go back a couple versions.
Actually, I'm on 4.0.1.
Yeah, but I was on the beta release or the nightly release, but I backed up to 4.16 and it still exhibits that same issue. So yeah, I'll try some other versions prior to us regrouping for a CMRI hangout.
Okay.
Yeah, I'll just go back to an earlier 4 release than what I was using for it. But anybody who's interested really ought to do just a little bit of Googling on CMRI, because it's kind of the bread and butter of what we all want to do with our railroads, especially with our Arduino. So CMRI is just the bee's knees.
Yeah, I was telling the guys that night that, you know, this is the holy grail that I've been looking for. And when Chris made that post, my eyes lit up, and it took me a day to be able to go back and look at and, you know,
Me too.
download it and take a look at what but as soon as he did, I got back on. I said, we got to hang out on this and try this out, because this is what I've been looking for.
Absolutely, me too. It was right up my alley, and it's just perfect. It's everything I've raved about LCC battering for, and it's here now and very economical. So
Yep.
I'm all over it.
All right. So looks like Andrew fell off again. He must be still having connection problems.
No, I'm here.
Oh, there he is. Okay. Gotcha.
But it won't let me screen share because someone else is screen sharing.
Yeah, you're showing my screen.
Well, my little screen sharing button's not coming up.
Yeah, you're showing my screen is what you're sharing.
Yeah, but I won't let me do mine for some reason. Yeah, I'll try again. Come back.
All right, so let's go to Dave. Show us what you did, Dave.
All right. Johnny, you got me up? I did something very similar to what JD did. I built a full-blown grade crossing, and you can see what I'm going to do is I actually have two photo sensors here because I wanted to stick with what we had actually done.
Andrew, can you mute, please?
Pardon?
Andrew, can you mute, please?
And so anyway, I used the two photo sensors here, and I did something very similar to Andrew. And if you cover either one, I'm sorry, very similar to what JD did. And if you cover either one of these photo sensors, and I have a delay built in here to prevent false positives. There's about a 2-second delay. You can see the lights come on, then the gate comes down, and it's actually very tolerant. There's a tolerance built in here. You can see I'm covering and uncovering, simulating a train going over the opening between the cars, and to the point where too, if it gets onto the other side, now I could leave that sensor wide open, and now it's monitoring the other sensor, and nothing has changed. And as soon as the train is gone and we leave it, the gate stays for a little while, then it'll open up, the lights stay on prototypically for about a second or so after, and then they will go off. So there's a lot of timing that happens in all of that because it's watching so many things at so many different times. The way JD did it was a little bit different than what I had done. What I'm going to do is I'm going to go and share my code screen here. And give me a sec to get there. And can you see my code screen?
Yeah, see it.
Okay. What I did was I started out by being a coder that I am like JD. I decided I was going to build classes or actual libraries out of this. Remember, we used the servo library. And so what I did is I built my own libraries to help simplify the code for me. So I built one, the crossing light here. This just flashes the two lights on and off. That's all that the crossing light does, is handles the flashing of the two lights. I have I forget what the pinout there is for. I have a timer. This timer class is the one that's very critical to everything that happens in my code, because I could start a timer and say, run this thing for 3 seconds, and it'll flash those lights. For example, the flashing of the lights, I have it set up for 650 milliseconds. And so the timer is set for 650, and every time it hits that 650 milliseconds, it'll flip the light to the other light and then restart that particular timer. I had another class in here which kind of smooths out these photo sensors, because I don't know if you guys recall when we were playing with the photo sensors that that number bounces around a lot, even if you're trying to hold it real steady. It'll bounce up and down 5, 6, 7 points. And what the smooth analog pin does is that'll smooth that out. It takes basically, it reads the last 10 entries and averages them out so that that number bounces around a lot less often. It's just kind of slow bounce. It smooths it out, makes it easier to, or helps to prevent false positives, shall we say. Then I had built another class here for the delayed sensor. Remember when I cover it, it takes like 2 seconds before it'll even start. That's to help prevent those false positives. And as I'm blocking and unblocking the photo sensor, this delayed sensor is what's responsible for not closing the gate or opening the gate right away. And as soon as it sees that it's set for 2 seconds, it'll open the gate if it's one way or the other. That also kind of helps to prevent if somebody's doing some work in the area over one of the photo sensors, it won't accidentally trigger if they're just doing something real quick in and out. It kind of depends on a full 2 second delay before it'll work. Here I'm just kind of defining my sensors. I've got 2 sensors that I'm using, 1, 2 photo sensors. Then I have a separate main loop timer. That's another one of those timers. Overall, in the code, my timer, I'm using probably 4 or 5 timers going at any particular point in time just to keep track of different various things. But it's all done in libraries behind the scene, so I don't have to worry about doing that in my main code of the program. In fact, you'll see as I get to the main code of the program, it's actually not very long. Defined a couple of variables in here to keep track of information. I have a thing that I call gate status, and this is the basic operating sequence that I'm using. When my gate status is at 0, you could see the gate is up and there's no train. As soon as we sense that there is a train blocking one of the sensors for more than 2 seconds, it switches that status to 1 and the lights start flashing. After 2 seconds or a second, I forget what I have it set to, the gate will start coming down. And that's what status 2 is, where the lights are flashing, but the gate is starting to come down. Status 3 at the end will be the gate is all the way down and the lights are still flashing. When the train leaves the gate area, the gate will go back up at status 4. Status 5 is a short delay after the gate reaches the top. The lights flash for about 1 second and then they go off. Here's just a little bit of initial setup. Here's that main setup of the program. And you can see here's where I start setting different pieces of information. Like the crossing light, I set it to use pins 8 and 9. The flashing rate was 650 milliseconds. And then initially I'm just turning it off. I'm saying, okay, I just turned the power on to the unit, the gate is off. I have 2 sensors in here, sensor 1 and sensor 2. Those are the photo sensors. And if you remember way back, I think it was two lessons ago, when we were dealing with the photo sensors, we had a low threshold and a high threshold. I'm setting those here, and I'm also setting the analog pin 2 I'm using. The second sensor, I'm using the same thresholds, but that's at sensor A3. And once again, I set this delay in here. The sensor is set for a 2 second delay. If I change this number in here to like a 1,000 or even 500, then that time that I am able to cover that up to will shorten up or become longer based on whatever the numbers in there.
So Dave, that's changing the sensitivity of the photocells, right?
Basically, yes. You know, it's how much time, you know, if I wanted it only to have a half a second in here, I'd set it to 500 milliseconds. Here's the servo that we're using, setting a variable for gate to keep track of the gate, whether it's up or down, a couple of timers. Here's the main loop of the program. A lot of these different functions, like the crossing light, I have just a simple little update function. You just put it in the top of the loop and it says, okay, if the light is on, make sure that I flash every 650 milliseconds or whatever you have it set to. In addition, I have sensor 1 and sensor 2. They have an update in there. All that update does is go through and check to see if the sensor's blocked or not. You know, is there something covering the sensor or not? And then I have another one down here, update gate, which is actually written in the main program because we were dealing with servos. That's just right down here. So that's not in a library yet. It will be shortly. I put in a little bit of debug code in here. One little trick you guys might want to know or might want to keep track of is, if you remember at the beginning, we have these pound includes. There's also a thing called pound define. And in this case, I set debug mode off. But if I turn that on, I can come down here and that will now include anything that's inside this pound if def section. If it's not, it will basically ignore it. So that's one way to include the debugging code that where you're writing to the serial monitor to watch things. But eventually, when your final code is done, you don't need that sending all that stuff out to the serial all the time. So you could just turn it off and not have to actually worry about removing all that code from your program. So that's why you see this pound if def debug mode on off. Whoops, undo that.
All right, well, that's some pretty good stuff you did there, Dave. And once again, we took another, computer programmer, gave them an Arduino, and they went nuts.
Yep.
Sounds like
I wanted to go through real quick on that switch because we had a comment on that a little bit earlier. I wanted to show you how I coded that switch statement. I use that gate status that we went through up above, and when the case is 0, when the status is 0, then it's right in here. It's checking the status for the gates to see if it's either one of the statuses is true. If it is, it starts turning on the lights and starts the whole process and sets the status to 2. So it starts it off and sets this, progresses the status to the next status. In status 2, once the main timer is done, once this timer is done for 2,000 milliseconds or 2 seconds, it hits case 1, which is to start bringing down the gate. And I have a little set in there that says bring down the gate, and then it sets the gate status to 3, and so it just says start set bringing down the gate. The next status 2, says, well, the gate's still moving, just ignore it, but if the gate's no longer moving, advance the status to 3. That's kind of a built-in delay to wait until the gate gets all the way down, and as soon as the gate is all the way down, it advances the status to 3. When you get to 3, it stays down, and when it finds either of the photosensors is no longer blocked, the train is left, or should I say, if both of them are open, what I say here, the gate is down and the lights are still flashing, wait till both sensors are clear, and then start putting the gate up. Advance the status and wait for the gate to finish going up. In 4, it just kind of waits for the gate to go up. When the gate's all the way up, changes the status to 5. When it's status 5, it runs the lights for another few seconds. 1 second, I said. When 1 second is up, it turns the light off. And then it's done, and it sets that status back to 0, which means there's no trains and the gate is wide open and cars can go through and so forth, so on. And that's basically the whole program. I do intend on publishing all these different classes that I have written and include libraries so that you guys can take advantage of them yourselves. I need to add more documentation for it so that you can understand how to use it. And once I get that done, I will put that out here on Hangouts for people to use.
So that, okay, so we got a comment.
Yep, got a comment. First off, let me get back up here to Brunette 42. He's having audio video issues. That could very easily be in your internet, but if you put your cursor on the viewer, make sure at the very bottom there towards the left hand side you'll see the word live. Make sure that has a red dot in front of it. If not, click on it. That'll refresh your viewer and bring you back up to real time. Okay, yeah. Timothy is asking any posting of the code snippets to the Facebook page as files. So I guess if somebody could post that on Facebook, the scripts.
Okay.
Or sketches. Excuse me, sketches. Also, YouTube Model Builders, we've got a tab on our YouTube Model Builders YouTube page for the Arduino. So anybody that's interested in these sketches, they are posted right there so that you can see them and copy them and be able to use them for your own use. So be sure to check.
On the Google Plus community page, we have an Arduino/Raspberry Pi page too. So
yeah, so we are posting those up. So
and the really neat thing about what Dave is doing is I know that was pretty elaborate what Dave did too as a computer programmer, but because he made those libraries, all you're going to have to do is to use his code is build your circuit, using your wires and your LEDs, copy his libraries down and run his sketch, and you'll be able to thing he did without having to know anything about it other than downloading the libraries and uploading the sketch, wiring up your circuits. So that's pretty cool. Thanks, Dave.
Yep, you're welcome.
Johnny, did you have any more?
Yeah, Robert was asking what's the difference between Arduino and Raspberry Pi.
I'm gonna send that over to Andy, but in a nutshell, Raspberry Pi is like a computer where Arduino is just an input-output device.
Yeah, think of that's pretty close to accurate. A Raspberry Pi is a full-blown computer. It's actually closer to being a smartphone than anything else because it's on the same processor. An Arduino is, and a lot of people are afraid of Arduino because it feels complicated, like you're programming a computer. It's not. It's a board of a bunch of switches. If you'll think, and it has a little more than that, but if you'll think of it as just a bunch of programmable switches, you're much closer than being a computer, because it is not. An Arduino is not a computer. It is just a bunch of programmable switches.
Yeah, or they call it a microprocessor, but it's basically, everything we're doing with the Arduino is an input or an output. You push a button telling it to do something, and then it just, according to your code, does an output like light an LED, buzz a buzzer, or something like that. It's input output. That's all it really is. Where the Raspberry Pi, like you said, you can get all the peripherals for a Raspberry Pi that you can hook up to your computer.
And a Raspberry Pi is in some ways overkill, but it's also not really good at timing per se. A Raspberry or a Arduino is very predictable to say, when this happens, do this, or when this condition is met, do these three things in this order with this delay. Whereas a full-blown computer is not great at that because it's not perfect at that timing. So for what we're doing, Arduino is absolutely perfect. If you're looking at something to drive a monitor, or even run JMRI on, I hope we get into some Raspberry Pi stuff in the future, because running JMRI on a Raspberry Pi is just perfect, just a win-win. But it's a Raspberry Pi is not very good. It can do it, but it's not very good at turning things on or off.
Yeah, that's
Well, and I guess the other another good.
If I can
go ahead,
interject, I agree. I look at it this way: Arduino is actually designed to interact with the outside world with lights and switches. That's what its goal and purpose is in life. Whereas
Absolutely.
the Raspberry Pi is actually designed specifically to be an inexpensive all-purpose computer.
Yep.
And is
human
not necessarily
interface.
designed to interact with the outside world with hardware.
Yeah, Arduino is like a machine interface, where a Raspberry Pi is like a human interface. Going back to what Andy said, an Arduino is so much better for doing mechanized, repeatable things over and over, whereas a Raspberry Pi is kind of like your PC. It depends on your input, typing, mouse, whatever, or running a program, but usually those programs depend on continuous input from human.
Absolutely. And Robert asks, so you could piggyback an Arduino on a Raspberry Pi? Absolutely, you could. I am, in fact, doing that. I'm using Raspberry Pi for my JMRI core system, because it running all that software, the Java and stuff that JMRI runs on, that's the perfect use for that. And then I'm using Arduinos for my DCC system and for signal systems and all this other stuff that we're learning here with Chris. So they work very well in tandem. It's just about finding the right tool for the job, and Raspberry Pi has its use, and Arduino has its use, and there's some crossover, but I think you're going to get into more pain than it's worth if you try to make them do a job they're not perfect for.
Okay, thanks. So we'll give Andrew one more try, and then we'll get into some buttons. So Andrew, what you got there? Give him a second to unmute and come back to life. There he is. I see action. Nope, I see Dave's screen again. Looks like he's still having. Yeah, you're muted yet, Andrew. Looks like he's still having technical difficulties. So what I'm going to do, we'll give him about 30 seconds more, and while he does that, I'm going to go out and a link, which I lost when I had. I'm going to give him a couple seconds while I go out and open a browser. Or I lost it, so share a link with you guys for our first exercise. As soon as my browser comes up, and it's running really slow again because I have all these things open. Arduino IDE, and of course the Google Hangouts. So if you don't want to wait for the link, you can Google Adafruit. Find it faster than I'm going to get there and get the link posted. And come on. You can, if Andrew can figure out his, or if my browser will catch up first. I think this could be a. Okay. Yeah, I'm not sharing yet because I'm trying to. Quite yet because I had to get this link to come up. Boy, even with the. It's all processor now because Dave came and helped me hardwire in my internet, so. I'm almost there.
I think Andrew's got it up.
Okay. I got the link finally. It's exactly the one I want. There's actually, okay, I just pasted the link in the chat here. I don't know if that goes out to YouTube. If it does, you want to go ahead and copy that and paste it for me, Johnny? If it does not, only the panelists will see this link, or if it goes out to YouTube too. Okay. Is there a way for you to copy and paste that for them?
I'm screen sharing it.
I'll take care of it.
Okay. So basically, I'm going to start screen share unless, oh, looks like Andrew's in business. Let's go to him before we go to push buttons.
Yeah, no, every time I go to screen share, I lose my connection. I'll try one more time. If it doesn't work this time, I'll catch it on the after show.
All right.
Oh, no, it's not going to do it. I'll get on now. Track coming up. Screen.
Yeah, without, we
well,
can see your Arduino. So.
Well, basically, what I've got a panel with 4 buttons on it, and in the hole an LCD display goes, which is now the power's gone off on it. So I could either throw 2 turnouts either end of a passing loop, or by just pressing one button, I can set it to passing loop, throw both of them at the same time for passing loop, or throw them the other way for the main line. And I've got tri-coloured LEDs to indicate which way the turnout's thrown. And I'm just my actual loop is only about 3 lines of code, and then it calls a function to see if a button's been pressed. If a button has been pressed, it sets a 1 and does that code. If it hasn't been pressed, it ignores it and goes on back to the loop. We just keep going around until a button's been pressed. That's my delay loop. And if I press button 1, it'll throw turnout 1. If I press button 2, it'll throw button 2. If I press button 3, it throws both turnouts. If I press button 4, it closes both turnouts and changes the colours of the LEDs accordingly. Let's see. No, all I'm getting is what's named crossing.
Yeah. Well, that's pretty cool. I like that because that's something that all of us can use.
But what I've done, I've broken everything up into functions, and I've got them on a separate tab in Arduino. So rather than have all the code on one page, I've created a new tab and I put my loop there. I have another page for my read the keyboard. I have another tab for my setting my roots routine, and another tab for switching my turnouts, and another tab for any messages I want to post on my LCD screen. The other thing is, when you go to do your buttons, I don't use a resistor for my buttons. I use the inbuilt pull-up on the Arduino instead. But all you have to do is change one bit of part of your code where you say set the input to an input. You put it to input with a pull-up, and the Arduino knows that you want to use the internal pull-up. I'll post the code for people to have a look at, and they can look. But no, I can't share screen.
Okay. Well, thanks. That looks really cool. Look forward to seeing the code for that because that's something I'm definitely going to try too.
Yeah.
Turnouts and.
Yeah. What I've done to make it easy to find a problem in my code, I got each block of code on its own tab in the Arduino IDE. So if you've got a problem with your routes, you just click on that tab and all your code for your routes is there. Or your problem with your turnouts, you click on the turnout tab and all your code for your turnouts is there. So you haven't got one big page full of code that you've got to stretch, you've got to scan through.
All right. Very good. Thank you, Andrew. All right. So Johnny, if you want to, I've got my screen shared. Do you guys seeing the Adafruit webpage I have up? Okay, so before we start on the push buttons, I want to show you this because normally you would think of push button as having two legs, you know, basically just power to one and ground to the other. And when you push the button, it connects. But if you notice the push buttons you get with your kits, they all have 4 legs on them. And this diagram here is a good way to understand why it has 4 legs and what they actually do. So if you look at leg A, we'll start with, let's say we're putting 5 volts of power onto A, straight across to D. So if you wanted to connect something else that was not going to be switched, that you always wanted to have power, just kind of passing through the switch without being affected by the switch, you could connect it to D. And the same thing with B and C. You notice there's a solid line between B and C, so that if you put power or a ground on there, it's going to pass through uninterrupted by the switch. That all the sketches we do tonight are going to have basically like in on A and the ground going out on B, so that when you push the push button, it makes the connection and the power can go from A through the push button back B to the ground. And you can also connect something to C or D, but most of ours will have, actually on B, it's gonna go back through a resistor to ground, and then C is gonna be the actual connection to back to the Arduino. So I just wanted to show you this so you understand it. When you take that push button in your hand, you notice the way those legs are bent a certain way. If you go match those up with your solderless breadboard, you'll see there's really only one way it'll go. If you try and bridge the center, and maybe I'll just stop sharing and show you my screen again that you can see this. I should actually take apart my other project here, but you can see that it's got the legs and they're kind of bent in an arc toward the center. Well, those will span across, you know, if you want to bridge across the middle of your breadboard, and they fit just right. If you turn it the other way, they don't fit. So that's how you know kind of like which is A and D and which is B and C. Look back at that web page, and I would recommend keeping this link until you get good and familiar with using these push buttons. So this is a really good guide right here for when you start using push buttons. If you forget, just come back to this page. It shows you A, B, and C in the picture, and then it shows you in a diagram. So basically you can just take that and push it down into your breadboard, and there's only one way that it'll do that. So
yeah, one thing you got to watch with those things, and I've got caught before, depending on which brand you get, they're the other way around. So just
okay.
you got a multimeter, just check which ones where you got permanent continuity and which ones where you haven't, and they're your pairs. Because I got caught, I had a box full of them, and half of them were different brands, and they were the other way around, and it caught me big time.
And I'm thinking, I'm just trying to look on the bottom of mine here to see, sometimes it may be marked on the bottom too. Mine looks like a plus sign. Maybe it's not. Yeah, it looks like it's on one side. It's got a plus sign like between the 2 legs. So anyways, I'm just going to go ahead and stick that in there. Your button may also end up looking like, hang on a second. In here, there we go. Yeah, your button may also look like this. It's just the same. It's the same button as one of these. I just simply. So if you want a smaller button without that big head, a lot of times you just pull the cap off and then you got a smaller button. That's a little trick I learned here. So actually they taught me that when I got the bag of these buttons, none of the caps were on. They were all in a separate bag. So I had to put them all together when I got the kits. All right, so the first sketch we're going to do, we're going to go back to our favorite Arduino website, which is Arduino, www.arduino.cc. And while I bring that up, I'll get that started and then I'll share my screen. Going to this website by now, I would think, if you've been using your Arduino much, or training and practice runs on different things. Screen sharing while I wait for the okay, bring up my browser. Slowly but surely it's filling in here for me. All right, yeah, I've still got the blue circle of death there. So, all right, so under learning, go to tutorials. And then under built-in examples, sorry, this is so slow. Figure out where that went again here. Under number 2 digital, scroll down to number 2 digital, and there's one called button. First, we're going to look at the tutorial, and in the meantime, while you're waiting, you can also open up your IDE, and I'll show you that right now, how we do that. We'll just go back to our file, examples, basics, or digital, and button. Open the sketch for you that goes along with this tutorial. And this is a very simple one. You see, all it's got is a button and a resistor, and it's got way more wires than you really need. If you look at this schematic, they have power coming off of the 5-volt and going to the power rail. Then way at the end here, they have another connecting back to the other power rail, even though there's nothing on that rail. You do the same with the ground, so you can absolutely totally ignore these 2 wires over here. Then they're also just jumping from the power rail to one leg of the push button, and then the same thing with the ground, from the ground. So you could actually take your power wire and connect it right to where this one is, take your ground and connect it right where the other one is, and skip these other 2 wires too. I mean, you got 6 wires where you really only need 2. I can understand they're teaching you for later on to practice using the rails and powering them all the time, but if you don't want to do 6 wires, you can easily just do 2. So all this circuit is really going to do is, it says when the button is open or unpressed, there's no connection between the legs, like we looked at in that diagram. But when the pin is connected to ground, as in you push the button, or I should say it reads low if it's open. When you push the button and press it, it makes the connection and puts 5 volts to the pin, and we read high. And all really, if we go back to our IDE and look at the sketch, all this tells you is it's going to turn on and off our famous little pin 13 light on our board. So if you just go ahead and upload this sketch, use your upload button. After you disconnected everything else from your previous projects. This is where it's time to start thinking about buying a couple extra Arduinos now, so you can leave a project or 2 set up and then start playing with a different project. So while I'm waiting for that to compile, I'm just going to switch back to, I wanted to point out that you see this nice little circuit diagram. You see these on a lot of web pages. This comes from a Fritzing. If you go to, I think it's www.fritzing.com.
Says it right underneath the picture.
Right. This was something, this is what JD alluded to earlier. He had it all, tried to do it all in Word, and he had it done. But then I mentioned the Fritzing, and he went out and made that beautiful little diagram he showed you earlier on using the Fritzing. So it's basically, you go on there, it has all
Word. I never went to Fritzing yet.
Oh, no, you didn't.
No.
Okay.
Sorry.
But all these diagrams you see here come from fritzing, where they basically have the picture of all the components in the breadboard, and you literally just drag and drop wires from the connection to connection, and then you can bit to where you want for a nice clean diagram, and then you could literally print a circuit board off that later on if you wanted to. So yeah, I'm still uploading there. It's finally done. Okay. So if I quickly go back and build, and I'll build it live for you so you can watch with me. Stop sharing, open up my page. So we need basically showing us we need a power button or power wire from 5 volts. Get over here is under the camera so you can see this. So from 5 volts to one of the legs of the pin of our push button. And we need a resistor, which the value was 10,000 ohms or 10K ohms.
Which is brown, black, orange.
Okay, so let me grab one of those. I had one laying here recently. So now on the leg applied the power, stick one end of the resistor in there and then pick another row somewhere else on your breadboard that isn't already being used. And then you just take your ground from that row back to a ground pin on your Arduino. So at the end, it's all you really need. Hopefully that resistor will show up fairly good. But all I'm doing, if I take my little handy dandy pointer, I put my power in on the one corner right here. Then you come across on the same side, connect the resistor to that leg, and then take that resistor and send it to ground. On the opposite side, we have input we need to put in there yet for the code. And if you look at the picture, it shows you on the same side as the ground, you take a wire, and that one is going to be connected to pin number 13. So 8, 9, 10, 11, 12, 13. So make sure I get the right one. But now, if all goes right, I should be able to push the button and turn on my light. And it's not working. Oh, I see why. My button didn't seat real well. And I don't think I got the right leg in the right hole. This again. Hopefully you guys are better luck than I am. But, you know, true to form, I didn't do this ahead of time so that I could work on it right along with you guys. Right along with you and make mistakes right along with you. That's how we all learn. Best way to learn is by making mistakes. It works. Let me make sure I'm centered in the camera here. Yeah, for some reason there it is. My Hangout keeps flipping away from me. So now you can see that as I push the button, LED 13 is lighting up. So it's pretty much that simple for a single button. You know, it's a little more elaborate just because of the fact that you're using the resistor and the fact that you're connecting the 3 legs out of 4. I wanted you to see that concept to start with of the 4 legs and what they all actually do. So is everybody caught up and working? I'll pan around, Johnny, and then take a look on the panel, see if we are out on YouTube land, see if we have any questions, comments, concerns. Okay, so what I'm going to do, if ever got her working, JD?
Not quite.
Just as a
Alright,
side note,
okay.
you guys are going to want to watch the green pin that Chris is showing there, the green wire. Make sure you have it set to the correct side, opposite side of the button as the red wire going in.
Right. Put it on the side
Same
that's
side as
grounded.
the resistor going to ground, yeah. So I made that mistake. I put the wire on the wrong side, and my light was constantly on, and I didn't know why. But that's because if you
And
look
we're
at
actually-
the diagram, it was straight through power.
So what that resistor actually does is it forces it to be a true ground. When you push these buttons, device, and it's got slop and it's got error like anything else. So it literally makes sure that it's fully grounded. You know, when I connect the button now, my power is passing through from the positive across the button and then out through the green wire because it takes the path of least resistance. But when the button is not being pressed, the power is still going through the button, or is still grounding back through the resistor and causing it to stay
What's happening with the
below the
circuit?
threshold.
It's either going high or low. That's what it's being forced to.
Right. So, anybody need a little time yet? Anybody need trouble? They're having trouble?
Pin number 2.
Yes, it's
The
pin number
website
2.
shows. Oh, yeah. Okay, see, I attached to pin number 13. I didn't even read that. I was looking, try attaching to pin number 13.
Yeah, I'm on 13.
I don't know. Mine's working on pin 2.
So I'm going to try that right now. I'm going to go move to pin number 2. That still works on pin number 2. Well, that's probably just backfeeding right through 13 because I was plugged into it. Scroll down. I'm going to share my code, and we'll scroll down and examine the code and see what we can learn. As soon as I screen share here, we'll take a look and see what JD's got going on there. We'll just kind of work through the code too. And all right. Actually, I can't see JD now when I do this, can I? There we go. So Johnny, do you want to put JD's screen up for us? Okay. I'm not seeing it right now. I see Johnny. Oh, it's probably because I'm screen sharing. I better stop sharing. Okay. So you should have positive going to, and what you want to do too is look carefully at the legs on the pin because they're not out at the corners where you think they are. They're off, actually all inset one row from the corner. So you may have, if you're just assuming and putting it in a row that lines up with the corner of the push button.
No, I'm trying to match it up to the leg. So let me walk you through. The yellow is the positive rail, 5 volt, and the black's the ground on the negative.
Okay.
And then I've got this on the positive, and I'm right next to the pin, on the corner pin right here.
Yep.
And
so far so good.
Okay. And so the resistor is on the same inline rail with this pin. I know it's not in the corner, it's just 2 notches over, and it's going to the negative here.
The ground.
To ground.
Yeah, that's correct. That's
Right.
a 10K ohm?
Should be. And if it's not, that's maybe my problem. And
then when
so
you
might be a 1K. I'll have to double check. Black, brown, orange, I think, on there.
Yeah, brown, black, orange.
Or brown, black, orange. Yeah. So
Okay.
this pin is connected to this corner leg here, and it goes to pin number
Right.
2. I had it on pin 13 going to 2.
Should be all correct. Did you upload your sketch?
No, that's what I didn't.
That'll help.
That might help.
Details.
What do you think?
Don't you love
Ask me how I knew that. Yes, I have done that more than once. Get all done, you get excited after building it, and it's like, hey, it's not working. Oh, helps if you upload your sketch.
Wouldn't it?
When in doubt, start back at the beginning.
That's what happens when your Arduino window disappears. The IDE window. Okay, done uploading. There you go.
Ta-da.
Ta-da!
Super. Somebody jumping in there?
It's probably
Chris,
me.
Oh, okay. All right, so let's go on to the next sketch, which is called digital serial read. And what this is going to do is basically take that same button, and we're going to, which we haven't looked at for a couple episodes now. So if you go ahead and, whoops, sorry. All right, again, File. Basics this time, and then digital serial read, or digital read serial. Open that sketch. We don't need to go to the tutorial. You could if you want to, because it's right on that same page where we were, just up a little higher. But you can just go ahead and leave everything wired exactly the way it is and upload this new sketch called digital read serial. Exactly the same. We don't have to change anything on our Arduino or our breadboard. All this is going to do is basically, rather than lighting up pin 13, or in addition to lighting up pin 13, serial monitor and read what the push button is telling us when we push it. Okay. Thank you. So as soon as mine gets done compiling and uploading. And I did figure out it's just mostly the processor on this wimpy computer that the streaming for this show sucks up so much of the processor that even simple things like compiling a sketch, if I would jump out of this Hangout, it would compile in about 5 to 10 seconds. So I'm just maxing out my processor. Your computer. So if any of you other guys are already at this point, no, I wasn't actually screen sharing, was I? I was thinking I was. So Annie, why don't you just jump around and see if anybody's got one to show that's working, or want to share their screen and show the serial monitor.
Yeah, mine's off the screen.
So were you able to,
Right.
anybody successfully done already ahead of me that wants to share it, do a screen share and show the serial monitor reading what happens when you push the pin? Otherwise. Oh.
Lost.
There's really not a whole lot we need to look at pushing the buttons. So what I'm going to do is go to Tools, Serial Monitor. And as you see, there's nothing but a bunch of zeros. When I push the button, those zeros change to 1.
Chris, you're not
back
sharing
to 0.
You're not sharing your screen.
All right, let me try my screen share again. I guess it was unsuccessful. again. Close a couple of these quick while we're. I'll reopen my serial monitor. Now can you see it?
Yep.
Okay, so what's happening is this looks like they're just sitting still, but you look at the bottom one, you can see it's flashing. This is rolling by zeros really fast. They all change to 1. So it's just pulling that pin constantly in a super fast loop. And they change back to zeros. So this shows you what's actually happening, and this is something you can use in your coding. You push a button, it throws a 1 instead of a 0, changes the value. You can make something happen like a servo throw, something like that. But this just goes to show high and low. This is 0. 1 means it's now high with 5 volts across the pin. JMRI basically works. It's all 1s and 0s, ons and off. Output device, and just like Andy said, it's just a whole bunch of switches on and off, and this is an example of one of those switches. And it's back on. So we'll stop that and we'll take a look. Everybody get that going okay? Anybody having any trouble?
No, I'm good, Chris.
Okay. So now we're going to go to another one real quick if everybody's ready. Just yell if you're not. We're going to use the same exact setup again. We don't have to change anything on our breadboard or our Uno. We're just going to load a different sketch. So go to examples. The 02.digital and pick on debounce. And I'm going to actually let, you could probably do a better job of explaining. He was explaining this once a week or two ago or one of our previous shows. So
Yeah.
And while we're uploading, I'm going to let Andy explain what debounce is, and then we'll go ahead and try it.
So the problem with a switch is you think of pressing that switch as being a single action where you press it. The problem is that if you go put the serial monitor on and press that switch and look at it, and you'll have to set your serial monitor to monitor real quickly, you will see that switch actuate numerous times because as you press it down, it may initially arc, or as the aptly named title of this function, debounce, is that it will bounce a little bit. So as you press that button, electrically, the Arduino is so fast, and that's what makes it so good at this. It's so fast that it reads numerous inputs. It may read 4, 6, 8, 10 inputs when you press that button down. So what you've got to do is use a little routine to sample that button and say, only set that as high if this timeout period has been set. In my case, I have my debounce set to 200 milliseconds, so that you have to hold that button down for 200 milliseconds, which is a fifth of a second, so no big deal, to get for the system, or the Arduino rather, to see that it was triggered as that. And you just declare those, and you set those as integers, or variables for log variables of time and debounce, and then call them later in your function, so that if now mine uses a set of states based on the way Dave was, but if you just declare this thing so that if time is greater than, this is all that matters about this for our purposes, set the debounce time, and if time is larger than debounce, and time is a variable you could set here, if it is larger than debounce, larger than this 200 millisecond timeout, then it sets that switch as being having been held down. That sounds more complicated. It even looks more complicated. But if you just copy paste those couple bits into your code, and then make sure you utilize them every time you expect that button to trigger a function. That's it.
All right, thanks. Yeah, so that's can be a little more complicated than just a simple switch that you think they are. Back in the screen share now and show you we'll just walk through the sketch real quick and then we'll try and execute it. If am I sharing? Okay, so this is the debounce sketch, and you notice there's a lot of gray matter at the top here. So they put a lot of comment in here to really try and explain what's going on with this. We got to scroll down quite a ways before we see any actual code in this one. There's very little. I mean, it's mostly just all comments to let you know what's really happening. But as Andy said, when you push a button down, it's not a clean instant on. I mean, it's when your Arduino is processing, like, what was it, Dave? 270,000 times a second it can run through a loop.
Yeah, I ran some tests and it was 270,000 times per second it would run through a loop. And what I did is I just simply counted how many times it went through the loop, and once a second I put out the answer. I dropped that down to 1 millisecond. You guys remember when we had that delay equals 1 or delay 1? 1 millisecond it went through that loop 278 times in 1 millisecond.
1/1000th of a second it ran through your loop 270 times. So now you imagine as you're pushing down that button and as the contact is about to make, it's not a perfect contact sense of time in a half a second or a second. You never notice the difference. It just goes from. But that Arduino, because it's cycling and polling that so many times, it's going to get a series of on and offs, and even a little electrical interference or electrical interference on your pins could trigger that. So you'll get these false positives, as those guys were talking about earlier with their sketches. So in order to prevent a false positive and having a light, maybe flicker on and off when you really should be off because you're not pushing the button, you put in that debounce. And all that does is delay it long enough to confirm that you actually pushed the button and it wasn't a false signal, or it wasn't a half push, or you weren't quite done pushing it. It's basically a fail-safe mechanism to say, hey, somebody truly pushed the button. So that, if we go ahead and read our debounce code, what we're doing here is just turning on the LEDs again, but this time I got done uploading mine. I'm going to go back and then so all mine is doing is each time I push the button, LED 13 either goes on or it goes off. So once again, so I'm going to go ahead and stop sharing and show you that. I just wanted to test it before I stopped sharing. And I can notice the difference right away from when you see my board now. You can actually kind of like feel the difference. In our first push button thing, I would push that button and that thing would be like instantaneous. Right now, when I push the button, you can almost see the delay of that light coming on, almost to the point where you can like feel it in the button. So,
and you can
the
turn
difference between this.
You can turn that time down. If it works okay for you at 50 milliseconds, I've tested it and mine seems to work okay at 50 milliseconds. But at 200 milliseconds, where I've got mine set, which is kind of the default from the examples, that's a very, very safe setting. But depends on what you're using it for. If you're using it to throw a turnout, then a quarter second's not a big deal.
Right. You can actually literally kind of like feel it when you watch the light, is because it isn't such an instant reaction. It feels like a slower reaction. But the difference between this sketch and the first one is this one, the first time I push it, it turns it on and it leaves it on until I push again and then it goes off. So there's two handy functions in this sketch. One is how to turn something on, hit it again. I mean, this is perfect for turnouts. Right, we go back to the first turnout with that push button. I would push the button, the turnout would throw, and as soon as I released the push button, it would come back. You want to use to push the button, throw the turnout one way, and let it sit there until I push the button again and bring it back the other way. So between that piece of code and the debounce piece of code, and we're not going to go through it too much because we're running out of time, but just examine this sketch here and you'll find two very valuable used for other sketches when you start putting stuff together. Turn it on and leave it on until you hit it again, and the other one being the debounce if you have any trouble with noise.
Also, for any of you guys that have seen Troy's video on using reed switches to throw your turnouts, this is the perfect code, and everything is identical for using reed switches or any other kind of sensors. This is a handy little bit of code to add to your repertoire.
Yeah, that's true. And, you know, I do recommend maybe Andy after the show, if you want to post a link in the comments section, even on YouTube to Andy's, to Troy's video. What a reed switch is just to digress a little, is a magnetic switch. When you put a magnet over it, activates the switch. And in this case, using a line of code like this, it'll stay activated until you put the magnet on it again and deactivate it.
Yeah.
And what he did was he buried these reed switches in his layout. So all you do is walk up and hover a magnet over it for a second, and it throws the turnout. So you got no push buttons on your fascia, no push buttons anywhere, no computer control. Strictly just walk around with a magnet on a stick like this, or in your hand, and throw your turnouts. Really cool stuff. Okay, let's go to the chat and see if we got any questions.
Yeah, we got one here from Robert. Does that keep the power flowing to the switch machine? Say if you're using a tortoise switch machine?
Yes, sir.
It would indeed. You know, because what you're doing is you're routing the power through the switch, and right now that power is just going continuously through the switch, and what you would do is to have another pin going out somewhere that was relying on this switch being on or off. So
I think you might be, Chris, you might be a little off on that. When you pull up on the button, the power no longer flows through that switch. It's the code in the program that does it, but your code in your program would turn the power on to the tortoise, and then your code would turn it off instead of turning an LED on and off.
Yeah, it depends on what switch you're talking about. The reason that most of us model railroaders, the real railroad, they call them switches, but in model railroading, we often call them turnouts. Biggest reason we do that is to obfuscate or to get around the confusion of talking about a switch as a button or a toggle switch and an actual turnout switch. So it isn't flowing through that physical button or switch, but it is maintaining power to the turnout. The Arduino is set to say go high and set that output of that pin to go high. That output will stay constant, and all you're doing with the push button is toggling that pin low, high, low, high. And if you leave it high, it will stay high. And I often recommend, if you're going to do a turnout, or like in my signal sketch that I've built, what I've done is specify the default condition when the thing first boots up, and then the button just toggles back and forth between those, because it doesn't have a defined state. Like a toggle switch has a defined state. If it's up or whatever. With this thing, it's going to come up whatever it comes up by default. So in your code, you should specify, when you first turn the layout on, where do you want the Arduino to set it to as the first boot up setting.
All right, Robert also says, so it would melt the crap out of a solenoid switch like the Atlas snap switch.
It would, but you could use a bit of code so that when you toggle it, instead of setting a pin high, you would set a pin high for 500 milliseconds and then set it low. So you would have three commands in series, and I can show you real quick. This is a really handy little side thing to be able to know how to do. If you want multiple code to happen on one line, you just specify a column. So as soon as my screen share comes up, what I do when I set it sets this pin low, sets this pin high, sets this pin high, and then prints out to the serial. But what you could do is say set it low or set it high, and then delay 500 milliseconds, set low. Simple as that.
Very good. That was very helpful. I hope that helps out there, Robert. If not, you can always back up and we'll go through it, you know, back up your YouTube and watch it one more time, and I think it'll make sense. I think it was pretty clear, so thanks, Andy. We're going to do one more real quick, and I think we're still going to use the same sketch. I got to double check that, but if you go to File, Examples again, 2.0 Digital, we're going to do the state change detection. Pretty much what this button was doing, I thought. Well, we were doing the button to do the state change, but I think, let's see, that's what it says here. Often you need to know the state of a digital input at all times, but you don't need to know the state of it all the time, but you just need to know when the input changes from one to another. For example, you want to know when a button goes from off to on. This is called state change detection or edge detection. So this example shows how to detect when a button changes from off to on or. So let's go ahead and load this, and then while it does, while mine is taking forever to load, then I will double check that we're using the same circuit, but for now I do believe we are, so our stuff, yeah, it says the circuit, push button attached to pin 2, 10K ohm resistor from 2 to ground, and then an LED attached from 13 to ground, or use the built-in LED on your Arduino board. Step here would be add to add an LED on your breadboard from pin 13 rather than that's on your Arduino. So you got your choice. I'm going to go ahead and, while this sketch compiles, I'm going to go ahead and sharing and show you. I'm going to quick throw a resistor on my board. I guess I wasn't screen sharing, was I?
No.
Apologize for that. I thought I was, so no wonder I can't stop sharing because I wasn't sure to start with. I'm just going to go ahead and take an LED I had laying here, and I put the shorter leg into ground rail, and I put the longer leg into one of the rows. I'll go ahead and grab one of my 300 ohm resistors. Over a bunch of times now, the resistors you need to go with an LED. I'll bridge the center gap. And what I'm going to do is I'm going to unhook my ground from the push button and put it on the negative rail. Actually, no, I'll leave that one there. What I need to do is the positive. So I'm going to unhook the positive from the push button, energize my whole rail up and down the side here. And I'm going to add two more jumpers, one from, oh, take that back. I don't need to do that. Right back in on the leg of that push button. I do still need to get power to this.
Here, you want to go to use pin 13.
Yeah.
And go to the LED, to the positive lead on the LED. From the positive lead on the LED, you could probably run it straight to
what
ground.
I need is a ground. Yeah, I need the ground to jump another ground across there so that I'm grounding both my push button and my LED. So if I go up into this row, I should do is energize my, oh, that button doesn't, there it goes. I'm going to go ahead and energize my negative rail. And then just jumper my push button back to that rail. There. So I'm going to let you guys all see if you can do this on your own, because this is kind of like combining things we've done a couple times now. I was just trying to work it out in my head without looking at the sketch, and that's why I was kind of fumbling around, but I think I got it. And I'll find out in a second when I
Pull the breadboard up even with the Arduino so you see the LED. There you go, right there. Just lay it down.
All right. So hopefully, see if my sketch is done uploading yet, and it is. So, just a button and nothing's happening.
Did you load it?
I think I'm not in 13. 1, 8, 9, 10, 11, 12, 13. I think I was in 14. Let's see what happens. Nope, that's not it. So I'm gonna.
See, now this is actually the
Go back
purpose
to
of this particular sketch, is to show you that why you need to use debounce. So I've got mine working, but it seems like just about every third press of the button, it'll turn the LED on.
Okay. Do you want to share his screen, Johnny, so we can see that?
I am.
Okay. You can see I've got a yellow LED on the circuit board, and I press the button once, pressed it, I keep pressing it, and it takes like 3 times before it'll go on. That's because it flips the state as soon as it sees something, and it's just not, that's why you need debounce, why you need to use debounce. That's what this demo was for, is to show you why you need that debounce, I think.
And it took me a while to figure out why this was being so peculiar, because I was not using the bounce, and I was trying to do a latching switch. Think of this as a latching push button, but
it is not.
Yeah. Oh, I know what this is doing. It's literally, you have to push. I remember now reading this, and I should have read through the whole sketch. You have to push your button 4 times before it goes.
Oh, okay.
But I think you're right. They're trying to simulate debounce as if, you're pushing your button and nothing's happening. But this is the one that they're talking about, remembering the state. But if you go back and read the sketch, and we're running out of time, so I'm not going to, I'll let you do that on your own, but you have to literally push the button 4 times before it goes.
Okay, yep, you're right.
So if you go back and look at mine now, I just took out the big LED and I went back to my normal 3, 4, on comes the light. 1, 2, 3, 4, on comes the light. Goes off on the first push, second, third, fourth, it comes back on, and it's going to stay on now till I hit it again. So that's probably what same thing you were experiencing, Dave. That seemed like it was a debounce issue. So the last thing that I was going to cover, but I'm going to let you guys do it on your own as homework, was going back to that Adafruit lesson 6 and work through that, because that kind of combines it all together. Screen real quick, and we'll go run out and just take a peek at it. I'm not going to actually do it tonight. Share my screen. Bring up. If you go to the Adafruit lesson 6, and I'm going to go back 1 page from this one. If you notice, it says Arduino code and other things to do. Push button picture. I'm just going to hit the Arduino code. It takes me back 1 page. It's actually the start of the lesson. And as I slowly get caught up, it kind of walks you through the whole thing with a little different code. The sketch defines 3 variables for 3 pins that are going to be used. LED pin. And they're actually using 2 push buttons in this one. And that's what I wanted to get to, because right now we've only been using 1 push button in each of these sketches. But this one will walk you through how to use 2 of them. And you can use them like in an on and off state. Or I think they even walk you through another scenario of using 2 buttons. So go ahead if you have time.
and I could show an example of it real quick because I have 4 buttons coded on mine. I could show that code very briefly if you
All
want
right,
to
I'll
see it.
stop sharing and we'll let you see that. And because we didn't, I was going to say we didn't get to your show and tell. So this is it, right? This is what you have
Yeah,
in mind?
but I can cover it just real quickly. So I wanted to quickly, as a proof of concept of some of these things, wanted to control this. So I put 4 buttons that I've used. Well, I'm using 3 of them. I've got the 4th one doing a weird thing with the sensors, but you could debounce to set that to a restrict, the bounce code to set it to a clear position, back to a stop position, and I disabled the optical sensors for right now. And I'll show you how simple. And there's 3 buttons in this, and I'll show you very briefly what the bit of code looks like, so you have an idea if you're on the right track. And I could share this bit of code, although it's very work in progress, like all of our stuff that we're working with right now. But this used states, so the signal actually has a state condition for. So what I'm doing is setting the clear to a state, and that state means something up here in the variables. So this is the state of clear, the state of restrict, and the state of the stop indication. Now I wish I could set a single state that was like 1, 2, or 3, and I'm working on a way to do that where you set the state to 1, 2, or 3. I've also done it with the serial monitor, so you could, and you could see this output as you press the buttons. It'll set that state, which you could actually use that serial monitor to drive a more complicated signal system, although CMRI is the right way to do that. Chris is, after we had the hangout the other day, Chris found a way to steal about 20 hours of my week last week by getting obsessed with CMRI like he did, I think. So, but all it is if the state of stop is low, then you set these states, and those states set the rights. And that's it's not more complicated than that. This looks more complicated because the way it is, but all of this is very repetitive. There's one little thing here that you need to wrap your head around, that bit of code, possibly, if you wanted to replicate what I've done, is wrapping your head around that bit of code. And then it's just, replicated quite a bit. And then there's some code to set the initial setting on the thing. Little bit of debounce code, set up all your pins, set up all your variables, all the standard stuff. But all of the code that makes all 3 of these buttons work is just 3 copies of that. That's it.
All right, can you leave that up for a second?
Sure.
Go back and highlight the time equals millis. Something we're going to work on. I'm thinking of for next workshop already. We've kind of touched on a lot of the input output devices that we would need on a model railroad now. LEDs, push buttons, servos, things like that. There's a lot of other cool sensors like the ultrasonic sensor and temperature sensors and things, but we want to stick to the things right now that'll help us with our railroad. And this little thing he's got highlighted right now is a very valuable thing that we need to learn, because if you remember our early workshops, we were using the delay command a lot, but the delay literally stops the entire process. Nothing else can happen on that Arduino while it's in delay.
Yes, sir.
And a couple of you guys learned the hard way working offline. You're trying to have this thing juggle 270,000 times through your loop a second. You can literally juggle hundreds of processes if you wanted to, but you can't if you use the delay command, because it literally stops the entire processor. It won't do a thing while it's sitting there. So this command right here is what's going to break that code for us. That's going to allow us to multitask, so to speak, to stop one LED for a certain amount of time, similar to using delay, but not stop it from doing other processes like throwing a servo, lighting other LEDs, etc. So
it's a very easy way to do multitasking. If you want to do something really complicated, there's other ways to do it, but this way is really easy.
Right. So this is something I really am thinking seriously about hitting up for next week. So if you want to do a little pre-homework and get yourself familiar with it, maybe even do a little project with it, go ahead. But I right now, that's seriously where, not next week, but the next show workshop 2 weeks from now. That's seriously where I'm leaning on going now, because we've kind of gone through the hardware. Now we really need to start our skills in the some of the shortcuts that are going to be really handy for us, like that.
Well, one other thing I
Without
want to
getting-
mention while I've got this bit of code up, there's a couple of these things. See, the best thing is to get a lot of use out of an Arduino. I mean, it's fine to drive a single LED with an Arduino if you want, but this time equals millis syntax here, like Chris is saying, what's so awesome about this is it would let you take a single Arduino and drive a bunch of LEDs and a bunch of structures and not have everything stop because you're doing one thing more complicated, like a welder over here and a bunch of lights, for a structure over to the side. That also relates to these multifunction bits. There's this bit of multifunction using commas, and this bit of multifunction using double ampersands, and those are slightly different. The double ampersands, and keep in mind that I'm mastering the details of this just as well as you guys are too, because all I've done is played with it a little while too. Is that the double ampersands is it waits for this state to get set, and then it goes on, and then it runs this one after another. But if you run the commas, this is probably overly simplified, but if you set the commas in there, it just runs them all at the same time. So if you want to set, say, 4 or 5 LEDs on at one time, but you still want to have them wired independently because you're going to control them elsewhere separately, you could comma them all, and it would just set them all high without any delays.
All right, so thanks for that, Andy. I appreciate that. There's one other thing, and I'm going to switch back or put it in front of my camera right now. This was the other thing I was actually thinking about doing. I was kind of a toss-up right now, so if maybe you guys tell me which one right now you want to do, but a shift register. And this is something that's going to allow you to run way more LEDs than you think you can off of your Arduino. But if you put one Arduino on each pin, I can't remember, what is it, 8 or 10 or something LEDs probably is all you can run off of one Arduino. But by using this shift register, it allows us to run untold number of LEDs off of there. So, and would you guys rather do the millis command there or the shift register? And I don't even know what the right name for that millis. I know what it does, but haven't really done it yet. I've just read about it. And same thing with the shift register. It's something I've been wanting to get to myself anyways, because sooner or later when you get these LEDs down pat, you're going to want to run more than just a handful of LEDs off of one Arduino.
Chris, I'm just thinking that the shift register might be more in line with what we've been doing, and once we're done with that, maybe go to the millis. That's just my thought.
Okay, well let's just make sure everybody then has a shift register for 2 weeks from now. If you don't have one that came with your kit, I'm gonna try and put that up close enough. 74 HC 595, and I think the HC 595 is the number they're commonly known by. So you go out on Amazon or eBay or any of your favorite electronics websites, you should be able to find those.
And Tony Fleetwood's asking, how many bits is that register? Is that an 8-bit or an 8 out, 8 in shift register?
That one is.
Yes. Yeah.
Yeah. And for all these guys, you could buy an 8 or a 16 or a 32 or whatever, and they essentially work the same way. So, and whatever suits your case.
You can actually daisy chain them together too for an unlimited number. So you could daisy chain 10 of those shift registers together. And
it isn't just LEDs. That's just where they're commonly used, because LEDs are something that are used in mass quantities. But you can literally run other things off of these too that you need, tons of, whether it's push buttons, LEDs, buzzers, servos, whatever.
Occupancy. Yeah, occupancy. You could take one Arduino and feed 200 occupancy sensors into one pin of an Arduino. So, my vote's on the shift register. Those things are just fascinating.
All right, so what I'll do is I'll do some studying on it, and I think if there's any of you guys that have used one before, I don't know how proficient I'll get with it in the next 2 weeks because I'm not going to have a lot of time to spend on it. So I might have one of you guys do a little auxiliary guest hosting next week if you're confident on your abilities with a shift register. So we'll talk about it during the week if we need to, but I'll see how far I can get. I'll start fumbling through it, and then if I get stuck, then one of you guys can maybe take over. How's that sound?
Fair enough.
Yes, sir.
Since this is beginners, for beginners by beginners, and with assistance of you guys. So, all right. Well, I'm going to wrap up the show for tonight. I appreciate everybody being out there. I know we ran a little long, but and we got a little deep on some of those awesome show and tells. It just goes to show where you can really go with it if you're intent on learning. I know a lot of that was over my head at the moment, and I'm sure there's other people out there sharing that sentiment, but man, I'm jealous of you guys being able to do that quickly. So Andrew, do you want to jump? Did you get a chance to do anything, or do you want to try it next week? Or you're muted. Can't hear you. Unmute yourself, Andrew. Nope, still can't hear you. Sorry. Nope. Can anybody else hear him?
No.
No.
No. Okay. Sorry, buddy. We can't hear you. So I'm going to go ahead and put a wrap on the show, and we'll get you back on next week, and hopefully you can get your internet issues figured out here. So, all right. Thanks for joining, everybody, and close her up, Johnny.
Okay. Thank you, Chris, for the show. It was a good show again. Had a lot of good participation there. Just want to say, go to utmodelbuilders.com. There you can check the schedules for the Tuesday and Wednesday shows and the Saturday live show. Tuesday and Wednesday shows are at 8 o'clock Central, 9 o'clock Eastern time. The Thursday and live shows are still 9 o'clock Eastern, 10 o'clock Eastern, 9 o'clock Central, 10 o'clock Eastern time. Trying to talk too fast. While you're there at YouTube Model Builders, if you haven't done so, click on the eMag and sign up for the notifications. That way when the eMag comes out, you'll be notified of it. JD and his crew do a great job. The eMag will be coming out this month. We got a new issue coming out. It'll be out sometime around the middle of the month is when JD tries to get it put out there. So you want to be looking for that. The next Arduino show is going to be on the 15th of March. So that'll be your next Arduino show. In between now and then, we've got Tuesday show, which is going to be with Bill the Track Planner. He's always got a good show too. So I want to say thank you for coming in and watching the show. If you did get a chance to watch the whole show, we did have a few people in here. They had to leave early. But these shows are recorded. Go to YouTube Model Builders on YouTube. And there you'll find our recorded shows in the playlist for each one of the shows. And you can go back and watch a recorded show as many times as you want to. So have a good night. Appreciate you watching. And we'll see you on the next show. Good night, all.